the story so far. We have a physical quantity called the action, which is the time integral of the Lagrangian, which is sometimes the kinetic energy minus the potential energy, but not always. But this thing called the action is minimized, and that's a fundamental physical principle that guides basically everything in physics. And if we have such a thing being minimized, then we know from variational calculus that the Euler-Lagrange equations must hold, in which case this equation here must hold for each variable. This object here is called the conjugate momentum of that coordinate. And we can use this principle and these equations to generate the equations of motion for physical systems in quite complicated situations fairly easily. Using those momenta, we introduced a function called the Hamiltonian, which is defined this way. And in terms of the Hamiltonian, the dynamics is extremely simple indeed. It is a set of linear, first-order, explicit differential equations. Let's do an example. Let's do a falling mass. Step 1 is find the Lagrangian in your chosen coordinates. This always requires a diagram. Basically, if you're going to describe your coordinate system, you're always going to want some kind of diagram. And the main thing I'm going to put on my diagram here is that this is the z direction. And notice the point of the diagram, I've pointed my z direction up. Otherwise, you could easily have chosen down for that. Okay. Now my Lagrangian is my kinetic energy, and I'll just do this in one dimension, minus my potential energy. And this is where my choice of sign and choice of coordinate becomes very important. Step 2, find my Hamiltonian. Now for this I'm going to need my momentum. That was easy. And now I construct my Hamiltonian. I only have one coordinate, so I don't need the sum there, minus my Lagrangian. Now z dot is just pz on m, so that's pz squared on m, and do that again, I get pz squared on 2m, and as we showed previously, that looks just like the total energy. It's very important when we do the Hamiltonian, we don't leave it in terms of z dot squared, we have to have it in terms of the momenta and the coordinates only. And step 3 is get the evolution from Hamilton's equations. So that has no derivative, I'm going to get 2 out of there, so I'm going to get pz on m, and my pz dot. There we go. There are my two equations of motion, which are extremely familiar. So I've got my momentum increasing due to my acceleration, free acceleration, and I've got my velocity is just related to my momentum. Thusly.